partly filled in by later minerals. Here's a Google Earth image of the crater itself. It stands out very well. You can see the town of Lonar there. You can see the sort of very greenish looking lake. That's due to algae in it. This was taken obviously in the dry season because it's quite bare and brown. You can see the green vegetation zone in the lake floor from seeping groundwater, which keeps it fresh. And here's some of the highlights. The alkaline sodium sulfate lake, as I said, a fan delta at the bottom of the river system that feeds down into the lake. This is one of the most interesting features I'll come to. It is also, from a management point of view, one of the major concerns, because you can imagine all the runoff from the town will tend to end up there. And not only do you get rubbish and so on, you also get a lot of high levels of nutrients into the lake, which contributes to the microbial blooms. Surrounding the crater itself is the ejector. Imagine the impact acting like an enormous bomb, blowing the crater. Material gets ejected out, it falls out on the ground as a thick layer, probably red hot or even white hot debris at the time, and it forms a distinct blanket, which you can see in the landscape. Finer material would have ended up much further afield, and as a general rule, ejector blankets in freshly formed craters go out for about 5 times the radius of the crater. So you have to imagine all of that area, whole of that area, at one stage being blanketed by this ejector material. It would not have been a good place to stand and watch too close. And here's a map by Maloof and his team of showing the ejector blanket, showing the different layers of lava and various other features. This is a cross-section, quite an old one from almost 50 years ago. A team led by Fredrickson with people from India and the US. They actually went out onto the lake when it was dry, and they're able to drill through the lake sediments. And you can see how there's this bowl-shaped depression continuing down for some considerable depth, over 100 meters below the land surface, 100 meters of lake sediments in the top, and then a range of materials called a breccia, which are rubble, if you like, of material fractured by the impact, blown up into the air, and then rained back down, filling the bottom 200 meters, 300 meters of the crater. So if you were to go there, this is what you would see. There you are. There's our team from our visit. This was back in early 2019. We were there. You can see the steep rim, and you sort of go sideways down that like a crab along a couple of tracks. You can see when you look across to the far side, there are a number of gullies in that wall formed by runoff and groundwater seepage. When you look at the exposures of the rim rocks, in the top right there, you can see that there are layers which are tilting, and they're not just tilted, but they're actually folded over. You can imagine a crater is like I don't want to be too revolting, but imagine it's like a blister on your foot or whatever, and it pops and the skin is folded back. And that's what happens during the impact process, that the layers of rock along the rim are actually folded back and overturned. And at the bottom left, you can see this conical structure, cone-shaped structure, which we call a shatter cone. And these are diagnostic of impact structures. We only find them in impact craters and the craters formed by nuclear explosions, where they're very, very high pressures generated that last for very, very short periods of time, a few seconds at most. We don't find them in volcanic craters. We don't find them in ordinary rock deformation processes. So if you find a crater that has shatter cones in it, it's very, very good evidence that this is in fact formed by impact. As I mentioned, one of the interesting features is the river that feeds into Lonar. It does get runoff from the town in the wet season, but most of the time it is actually fed by a spring. The spring now starts up near the rim in a temple, heavily modified. As you can see there, it feeds into that pool where those local lads are having a swim. And then it sort of spills down through a gully all the way down to a delta. And when you look at the floor of the delta, in the bottom right there, you can see there's all these rounded cobbles, large pebbles of material that has been washed down that valley and out onto the lake floor. All around the rest of the lake sediments are very fine, very muddy, but in that delta area, that fan-shaped area, there's a lot of coarse sand and there's a lot of sort of gravel and cobbly material. And in that photo on the left of the delta itself, you can also see the various signs of the lake rising and forming strand lines of shorelines over the last few months or weeks. And if you walk along the lake shore, and I actually show them back here, particularly along the eastern side of the lake, there are a number of seeps, groundwater zones where groundwater has seeped down out of the rock and into the lake. And so the ground where Analogue, one of my colleagues, who was there in both 2019 and late 2019, both times in 2019, the ground she's standing on is quite dry. If you were to get your shovel and to dig a hole, you'd find that the water is only a few centimeters below the surface and is still, pardon me, about 20 or 30 centimeters higher than the level in the lake. It's seeping out of the rock along the walls of the crater and down and filling the lake. And as the water comes into this seepage zone, it starts evaporating. And as it becomes concentrated, it precipitates out carbonate around the roots of trees. These are the tamarisk trees, which have now been cut down because they're a pest. And you can pick up pieces of rock, like the one that Analogue is holding there, and you can see all the filaments of the fungi and the root hairs and the shape of the root itself. So these are preservations as fossils of a lot of the biota that was living in these spring environments. And that is very important when it comes to looking at similar craters and similar deposits on Mars. Pardon me. Other features of the lake, the water level does go up and down for reasons that are not well understood over very short periods of time, like up to a few tens of centimeters. So you can see in the picture on the top left there, that was in late 2019. The water level has just recently fallen, and you've got this dark colored mud, which is very wet and sticky. But the rest of the crater floor just consists of these sodium sulfate, organic rich muds with clay and so on. And you may have seen in the news that periodically the lake changes color. It's normally sort of a normal and muddy water color. Periodically, it'll go green from algal blooms, and very occasionally it goes bright pink from a microbial species called Dunliella. This occurs all around the world, when the water salinity reaches particular concentrations. These microbes bloom in vast numbers, and they turn those lakes pink. There are compounds called beta carotens in these cells that make their color. In some parts of the world, people actually harvest them as a food additive. So if you list the features I've described here in the crater and look at the counterpart on Mars, you'll see there's a lot of potential analogues, counterparts between Lonar crater and what we see on Mars. So the decaying basalt is very similar to the Martian crust. The fossil soils are paleoenvironmental indicators for the composition of the atmosphere, the amount of rainfall and groundwater that's going on when those soils formed. On Mars, we would also look for similar fossil soils and weathering horizons. The crater itself provides an excellent analog for the sort of processes that occurred when Martian craters are formed. Their products and how those craters are then modified over time through erosion and sedimentation. The gullies, we see Martian gullies on crater walls as well. Some of these appear to be formed by just dry material rolling down the side. Others seem to be related to seeps or snow melt. And so by looking at the gully craters at Lonar, we can get an idea, a way we can compare them with the Martian ones and understand them better. The river, of course, we see rivers, dried up rivers flowing to Martian craters. We compare that. The delta is a great comparison for Martian crater floor deltas. And the lake sediments are an analog, a counterpart for Martian crater lakes back in the early Mars, when Mars craters had lakes in them for their mineralogy and chemistry, for their organics and perhaps biota. And there's an example there on the left. You've got the delta of Lonar crater. And on the right, you have the crater of Jezero crater, Mars. Lonar is quite small. The delta is only a few hundred meters across, whereas the one in Jezero crater is several kilometers. But there are similarities in the fan shape and the organization of the deposits, as we will see. So where is Jezero crater? This is a topographic elevation map of Mars. The darker the blue, the lower it is. The brighter the orange, brighter the red, the higher the elevation is. And where the colors go from warm yellows and oranges and reds down to cooler greens and blues is the datum altitude on Mars. Like we use sea level on Earth, that there is a datum altitude on Mars set originally by the average air pressure, because obviously there's no oceans on Mars. And Jezero crater is on the edge of a much, much larger impact basin, almost 1,000 kilometers across, and is on sort of the boundary between the very smooth northern plains, which are low level, the highlands, which are somewhat higher up. And it's a site which has considerable interest. So it was chosen as a landing site for the 2020 rover by NASA. Although it's a NASA mission, it's actually international. There's scientists involved in that from all over the world, from Australia, from various European countries as well. So just because a country has its badge on a mission doesn't necessarily mean to say that it's not an international mission. And one of the things it also carries is a little robotic helicopter, and more about that perhaps anon. And the idea of this rover, which is about the size, it's bigger than a tuk-tuk, it's about the size of an old-fashioned mini car, is to collect samples, analyze them, obviously take lots of photos, and then store those samples for eventual return to Earth. It's the first Mars sample return collection mission. So here's Jezero crater, almost 50 kilometers across. It's about 270 meters deep. It's impacted into Middle Noachian, which means roughly 3 billion year old volcanic rocks. An ejector from that large basin, Isidis Basin. And on the bottom left there's a much younger volcano. You can see the crater at the top. And the crater and the impact event has blasted a hole in all of these rocks. And its significance as a site, and it's why the rover was sent there, is not only is this diversity of target rocks, but there was a lake in the crater floor, which is quite so flat, and there's this delta feeding into it. And the 2020 rover, now called the Perseverance rover, landed there in February last year. And here are some of the highlights. You can see the volcano. You see the inflow valley, the river that's flowing into the crater, the delta that's formed. Unlike Lonar crater, there's also an outflow. So this lake probably did not get exceptionally salty, although it may have done if the water level was too low to flow out. And when we look at the rocks and the view of the rover, and the rover's camera is about the height of a tall person's eyes, this is what it sees. So if you're a tall person or you're sitting in a vehicle, this is what you see driving across the floor of Jezero crater. Rocks, sand, rocky pavements. And most of the floor rocks where the rover has been consist of mafic volcanic rocks which are basically basalt, either coarse-grained or finer-grained with little cavities in them, like some of the cavities we see in rocks from the Ajanta caves, for example. But interesting though the crater floor is, the main target is the delta. And here's a geological map of the area where the rover intends to explore. So the greenish material on the left is the high level plateau. The rover probably will never get there. The rim, where the rover may or may not get to, is in purple. The blue are the marginal deposits to the crater lake, and they are carbonate, just like the marginal deposits in some parts of Lonar crater. The delta itself is that sort of grayish, bluish color, and the basalt floor is in sort of pinky brown. Now, when you land on Mars, the engineering system has certain uncertainties. You just imagine if you're firing a gun at a target and you fire 100 shots, no matter how good a shot you are, the bullets will all land within a small area of uncertainty. And if you're doing the same thing, when you're trying to land on Mars, there'll be an area of uncertainty which your rover, your lander, will come down. That's called the landing ellipse, in there in bright green. As it happened, the rover landed where the star is, not too far from the delta. And in the last 18 months, it's been driving across the crater floor, taking samples, taking readings, and has started to climb up the delta rim. The idea is it will sample all the edge of the delta, across the top of the delta, and then to the marginal carbonate deposits that you can see there. And here are some of the views we get as we look across, as the rover looked across the floor of the crater towards the edge of the delta. The edge of the delta is a cliff. It's been eroded. And just like in a terrestrial delta where you have the lake floor deposits, which are thin and muddy and flat, delta edge deposits, which are inclined as sediments roll off the top of the delta and down into the lake, and then the flat, coarse sands and gravels of the top of the delta, we see exactly the same thing we see this at Lonar, and we see exactly the same thing here in Jezero crater. And this architecture of delta deposits holds true whether you're talking about a little delta, like the one in Lonar crater, or a medium-sized delta, like the one in Jezero, or really big deltas, like the size of the Ganges or the Indus deltas, which are hundreds and hundreds of kilometers across. They all have the same basic structure. And what that means is, as the rover works its way up the delta front, it can first of all sample the very fine-grained deposits at the bottom, which represent what was going on in the lake, the finer-grained deposits coming down from the delta, and then the coarse-grained deposits at the top. Now, I don't know if any of you have actually been to a dried up riverbed. Hopefully you have. And you may have noticed there's lots and lots of different rocks there. Rocks that may have come down considerable distance, perhaps tens of kilometers down the river to where you pick them up. And so one of the advantages of looking at those coarse-grained deposits at the top is that you can get samples of material from a much further away than the rover is ever likely to travel. So you can sample a much larger proportion of the area of Mars. And in fact, this image is a bit fuzzy. It's a telephoto image, but I hope you can see how the cliff in the distance in this rover image, and it's got a little telephoto lens, or quite a large telephoto lens that allows it to take it. There are these larger boulders on the very land surface itself and in the side of the cliff, much like we saw on the land surface of the Delta in Lonar, indicating there are this diversity of rocks that one day, in the next year, the rover will be able to study and perhaps sample. And here are what we found in some of the recent deposits. This is just off the crater floor. You can see the layered, flat-lying sediments at the bottom there, which are clay and sulfate-rich sediments, gypsum for the most part. And they contain significant quantities of hydrocarbons, organic material, particularly aromatic hydrocarbons, those that have ring structures in them. Now, these are associated with life, but they can also form by non-living processes as well. Pardon me. But anyway, the rover collected 2 samples from there as cores, and they'll eventually be returned to Earth to be studied in detail. Further up the slope, in the location called Skinner Ridge, he collected 2 more samples of sandstone. These are sands that have been washed down the delta and deposited as lobes on the edge of the delta. So we're starting to get an idea of how this basin, the crater basin, was infilled by sediments and the kind of material they're made of, and also the materials that may host evidence of life, such as organic matter. So if we compare these 2 sites now, rather like we did earlier with the analog potential of Lonar crater, we can actually now specifically compare not the potential, but what we've actually found at Lonar with what we've actually found at Jezero. The substrate's definitely the same. It's basalt. There is hydrothermal alteration, both in Lonar crater. Remember those sort of reddish hematite-rich pipes, and we've seen similar hydrothermal alteration into volcanic rocks at Jezero. They're crater wall gullies, both craters. They're marginal carbonate spring deposits. There's an inflow channel. There's an outflow channel at Jezero, which we don't see at Lonar. But everything else, the presence of the delta, the presence of conglomerates, the lithic sandstones, and organic rich muddy and evaporite sediments, all the same. So in that regard, Lonar is a very, pardon me, a very good analog, very good natural laboratory to help us understand Jezero crater on Mars. So, any questions? My voice held out.
Thank you, John, first of all, for giving us such an insightful presentation, and especially the last slide that you presented, which gave us a complete overview of how Lonar is similar to Jezero's crater. Yep. That was wonderful. Question as in, I would like to ask that you've personally worked on the site and you've carried out research yourself. So would you just give us a glimpse about what research you exactly did, and if people can find the research paper or anything to go through it, that would be great.
Yes. I am associated with the Amity Center of Excellence in Astrobiology at Mumbai. Where we have a team together. We have Siddharth Pandey, who set up the center and is now pardon me, doing more work at JPL. We have Jen Blank, who is part of a NASA rover mission. We have Annalie Beattie and myself from Australia, and we have a number of colleagues at the various Indian universities as well. And we have done 2 preliminary trips identifying the potential of the crater for this sort of research. There'll be a number of studies by Indian and overseas researchers of the crater, but they have, for the most part, not looked at the analog, the Mars analog potential. So we've set that up, we've published it. We applied for a NASA grant in 2019. Unfortunately, that was not awarded. And then, of course, COVID happened, and things are on hold. But now the things are opening up again. We would like to start that process once again of working there. The problem is, to do analog research, you've got to do a lot of analytical work. You may well have to drill holes in the sediment, and all this costs money. And someone has said, no bucks, no Buck Rogers. So we need to find funding for this research to go ahead. But since we've published all of this, what it means is, even if we don't get the funding to do it, someone else might, in which case the work gets done anyway.
True. I mean, the point you highlighted, funding is always an issue. But yeah, moving on. Also, you yourself have been part of various Mars analog simulations in and the Arctic research station. So how was your experience as an analog astronaut performing experimentation, and how it actually impacted you? Would you please highlight it so that people would understand how important it is to go out and do analog missions?
Well, that was they were somewhat different studies. So in 2016, 2017, I was part of the same crew of 6 or 7 people. Spent 3 months at a simulated Mars base in Utah, and then 2 months. Initially, we hoped to spend 2 months. We ended up spending just over a month because the weather wouldn't allow us to get in time. At one on Devon Island in the Canadian Arctic. And we were evaluating the operational validity of these 2 stations. Similar designs, similar crew. What are the strengths and weaknesses of that? And looking at other operational issues. What's an operational issue? It's basically how you do things, how you organize your time living in a Mars station. How much time can you actually spend going out and exploring your environment or wearing a mock-up spacesuit, as opposed to doing housekeeping and keeping the place running and keeping it clean? How much food do you consume? How much water you consume? These are operational questions. And there's great advantage to doing that, doing real scientific work, real counterpart to a Martian environment or a lunar environment, rather than just doing it in a shed in a laboratory, which you could also do. The location in Utah is made up of areas of clay and sulfate-rich sedimentary rocks, similar to what we see on Mars. There are actually ancient delta deposits there, although much larger than in Jezero crater, let alone in Lonar, but still interesting from that point of view. And it's very Mars-like landscape. It's barren, it's red, and it's a really beautiful place. The Devon Islands location is very remote. It's to get there, it's 2.5 hour flight from San Francisco to Edmonton in Canada, and then another 2 hours from Edmonton to Yellowknife, further north in Canada, 2 hours from Edmonton, from Yellowknife to Resolute, which is a staging post in the Arctic, and then 90 minutes from there to Devon Island itself. You really feel, and you are, on the edge of civilization. When you're on Devon Island, you're the only human beings for hundreds of kilometers in any direction. If something goes wrong, it might be 4 or 5 days before rescue can get to you. So it focuses the mind, and that's good. Scientifically, it's interesting because it too is in an impact crater. The Horton impact crater is quite large, 20 kilometers, 22 kilometers across, so 10 times larger, 7 times larger than Lonar. It's about 15 million years old, so 30 times, 60 times older than Lonar. Very heavily eroded. and in very different rocks, actually in fossiliferous limestone. So the rock itself is not a good analog. But the crater itself is an excellent analog for some we see on Mars. It's got lake sediments in it. It's got melt rocks melted by the heat of the impact. And the station is actually parked up on the rim. You've got a beautiful view across the crater. It's also a good analog because there is permafrost. The ground more than half a meter below the surface is frozen all the year round. If you were to go up to the high areas in Ladakh, you would find the same thing. 4,500 meters above sea level in Ladakh is permafrost. And that's one reason why Ladakh is an interesting Mars analog too. A lot closer to us than going to the Arctic. But anyway, they're the two sites. There were 7 of us in Utah, 6 of us in Devon Island. We're an international crew, people from the US, Canada, Australia, France, Russia, and India. Anushri Srivastava was our Indian representative. She's now finishing her PhD at the Open University in the UK. Wonderful lady. She's been working on lake deposits on Mars in the not in Jezero crater, but in the Gale crater where the Curiosity rover has been working. It'd be great to have her to come out and look at Lonar. Maybe she will one day. Anyway, we had this international team. I think all of us would do it again with the same crew. We got on very well. We worked very well together, and we've published probably about half a dozen papers on various aspects of our studies: the geology, the ecology, the EVA, the field operations, and so on. So we think we made a useful contribution there.
That sounds a lot of serious things to do, but with the fun factor involved. So, I mean, I enjoyed listening to you, and I would definitely like to go myself once and do the analog too. Lastly,
well, Amity University would like to set up an analog station in Ladakh. And some work has been done, and again, of course, all on hold during COVID, but the plans are still there. So maybe in a couple of years, there will be some sort of facility of that type in Ladakh at a place called Sokar.
Right. That sounds promising, I guess. I can look forward to it.
Yeah.
And lastly, I mean, I wouldn't like to take much of your time because I can see you're feeling a bit unwell. I would like to ask you, what would you like to say to the people who are looking forward to the Lonar expedition, as well as to those who are, trying to opt or take geology as a career and then get into the field of space exploration?
Well, first of all, be safe, right? There's no point going to any of these places and then breaking a leg or falling over into a thorn bush or getting bitten by a local dog, and it will spoil your whole trip. So whatever you do, always think safety first. And it's very hot in there. The slopes are steep. There's wildlife. There's wild pigs. There's monkeys. Don't think there's a monkey there. They like these temples. I can't quite see one in that photo. And they're big, aggressive monkeys. And there are leopards, and of course snakes and so on. So be careful. Second thing is enjoy it, even if it's outside your comfort zone. And if you're doing things you've never done before, drink in the experience of what you're doing, and be prepared to see things from a different perspective, to do things different to what you've ever done before, and learn from that. And even if you decide not to follow a career in this area, let that experience still enrich the way you look at the world. People who go on this trip may well use this to to inform career choices, which would be great. You may well learn new skills in the process, particularly if you're not used to going to relatively remote areas and working in difficult terrain. But that's all to the good. Nushri, my Indian colleague, when she went to Utah, she'd never been out of the city before. Actually, she went to Ladakh a couple of weeks before we went to Utah. Never been out of the city before. Never been at high altitude. Never seen snow. Never driven a vehicle. By the time she finished it, never fired a gun. By the time we finished that in Utah, she had done all of those things. Why did she have to fire a gun? Because we were training to go to the Arctic, where there are polar bears. And every time you go outside, you have two people doing the studies, but you always have one person on duty carrying a gun in case there are bears around. So, and she rose to that challenge magnificently. So don't be afraid if you have to step outside your comfort zone. Rise to the challenge, take on a new experience, and take it with you wherever you go from there.
With this, I guess we have reached the end of our talk today. And I once again thank John for your time, and you were unwell, but you still joined us and gave us the insights. I'm once again grateful for that. Thank you.
You're very welcome. Okay, see you later.
See you later.